Hi everyone, can you hear me?
Yes, okay.
Okay, thanks Lokman. I guess to respect your time, I just get started first. Like maybe, I don't know, maybe people are not able to join so much, but they can catch the recording. So tonight, I think there were some questions on tutorial 2. I just wanted to address that really quickly, but also to kind of remind you to prepare for test 1 and test 2. And I will go through some material on the last topic on aging. Aging is kind of a new topic that just recently introduced more material into this course. So I plan to go through some of the material that on aging that will be relevant to your tests as well as for your final exam and your PBL2 lah. I think in total, I think there's most people have submitted tutorial 1, so that's good. There's just a few that have not. Please do so. And some have and most also have submitted PBL1, so that's good. I would urge you to please get started on PBL2 because that's quite relevant to your test, your final exam, and it's not something you can get done in 1 week. I don't think so. So you need some time to work on that. So I've delayed tutorial 2 up to the very last day, 3rd December, just like a week before your final exam, to give you a bit more time. I'll just walk through it again, very briefly. Maybe I can start with that first. No, I think I'll start with the aging first, and then we'll do that at the end of the session. We won't have such a long session tonight, maybe I think an hour plus. The reason being, I'm anticipating to have another 1 or 2 more discussion session after your test 1 and your test 2. So because of that, maybe I just conserve a bit of the time. There's not that much on the aging anyway. So let's try to get started on the aging. Then I'll talk about tutorial 2 and some of the updates that I'm making. I think I had forgotten to give you the analog Python file. So I've attached it already, but I need to clean it up a little bit more. Then I'll walk through what I'm actually wanting you to do for tutorial 2, but that's only 5%. The main thing would be please prepare for your test 1 this coming Saturday, 18th of November, 2 to 4 p.m. Malaysia time. And test 2, the 25th of November, directly the week after, 2 to 4 p.m. as well. Test 1 will cover everything on the flow of the VLSI design flow, what the purpose of all these steps and all that. So completing tutorial 1 should give you a good understanding of that. But I feel that some of you haven't actually gone deep enough into the why, because your tutorial 1 answer was very shallow. So it might not be enough for the test or the exam type of response. I need you to really understand the purpose of that step and what are the inputs and what are the outputs from that stage. I might ask you to compare and contrast how is this step here different from another step or similar to another step. Okay, and of course, test 1 also include the critical path, identifying the critical path, estimating the critical path. And here, you actually have two options. You can actually read up the delay directly from the Liberty file. The catch is this semester onwards, I'm going to be a little bit more strict on the accounting for the load capacitance. So if you were to read up the delay from the Liberty file, you will get some marks. You'll probably be like a B plus, A minus, but you won't be able to get a full A. Why? Because the delay is also very dependent on the load capacitance, how many gates are connected at the output. So if you use the logical effort approach, you should be able to get a much better estimate. Or if you were to take into account all the gate capacitance, input gate capacitances, then maybe that will be fine, right? But you can't just arbitrarily. I mean, what I'm saying is I'm going to be distinguishing more accurate estimates of delay versus less accurate. So either logical effort, or you have to take into account what is exactly connected to that logic path and the delay with that. And of course, I think for delay, only the logical effort gives you a pen and paper approach to estimate, taking into account the delay, right? Because it takes into account the fan out and all that. So that's what's going to be slightly different. Of course, if you just take the delay of the gate from the Liberty file, you'll still be able to get about B plus or A minus, but you're not able to get the full A. Just to really drive home the point, you have to estimate delay, including the capacitance at the output. So that will be for test 1, and test 2 will cover the process variations, the near critical path, how to estimate the variance and the mean of the delay as a result of process variation that we talked about in the last session, and the aging that we will be discussing tonight. Okay, so if there's any concerns or doubts, please let me know in WhatsApp. But we are very rapidly coming to the end of semester. I think roughly another 3 weeks more only. So we should wrap this up as soon as possible. Okay. Right. Let me get started, and just interrupt me if you if they have any question. So I want to talk about aging and reliability. Basically, this idea of aging, we're talking about circuits that are changing over time, right? So last semester, last session, we actually talked about process variation. That's when you're manufacturing the circuit. What happens is you create maybe 10 or 100 or 1,000 of the same design. It's the exact same design, and you're making 1,000 chips, 2,000 chips, 10,000, 1,000,000, and so on. Although it's the same design, each chip would have slightly different delay or specification that's achieved because of variations in the fabrication process. What type of variation? Line edge roughness, variation in the oxide thickness, variation in the random dopant fluctuations, RDF or RDD. And then all these cause variations in the threshold voltage and also variations in the current, which leads to variations in the delay. So same design, sort of different chips emerge. Today we're talking about aging and reliability. When we talk about aging, we mean that you create a circuit, it achieves a certain specification or certain delay at this point in time. And you keep using and you keep operating the circuit, and over time, the specification or the delay changes. So that you can see by this graph. Starting point when you've just made the circuit, you could have recorded a delay, certain number of nanoseconds propagation delay or femtoseconds propagation delay over this NOT gate, right? But as the gate ages, that means you're using it 1 year, 2 year, 3 year, 4 years, 10 years, the delay increase because the circuit grows old, inverted commas. So there are certain effects that make it slow down. And you will see that the rate of slowing down the delay is sort of different for each gate. Some gates will have a greater slowdown. Some gates will have a less slowdown. And we're going to be analyzing what are the main effects of slowing down this gate. So there are two things that happen. One is the slowdown of gates, and especially it's just transistors actually, but that slows down the gate. So what happens is, as a function of age, the longer you use, we're talking in years, the delay will get longer and longer. That's why the delay goes up. And at some point, it might actually break the specification. So you start to see if your critical path delay starts to exceeds the max delay, then your circuit will not be able to function properly anymore. Of course, I don't think it will exceed the whole time, because whole time you need to actually, the mean delay, you actually have to reduce the delay. But here, most likely it's the max delay. You actually have max delay violations and things like that. That's the thing that you have to watch out for. Right. The second effect, of course, is what happens to the wires. The wires actually get damaged over time, and they lose their ability to carry current, and they sometimes at the worst case they just kind of disconnect. So there are two bad things that happen as a result of aging. One is the gates actually will get more and more delayed, and at some point, some of them will actually fail. This will be the dielectric breakdown. We'll talk about that. And the second effect will be the wires will actually degrade, and that also increases the delay of the wires, but at some point they may actually disconnect. They degrade, it reduces the ability to carry current and all that. Okay, but for this semester, I'm not going to be talking about the wire delays or the wire aging so much. If you're interested, you can read the textbook. It's two effects, self-heating and electromigration. These are delays associated with aging in wires, but we're not covering that in this semester. I think I like to really focus on the transistors and the gate level delays, because this is new material that we are introducing this time around. Okay, so the key idea is As you keep using these circuits, the gates will actually increase their delay, and they increase at different rate. And we're trying to understand how to really account for that. Okay, there are three major mechanisms, process through which the transistors will decay. So here you can see a diagram, a cross-sectional view of your MOS transistor. This is your source and your drain with the doping. Then you have your channel. So this is N, this is P, this is N. If this is P dope, this is N dope, this is P dope. Then you have your silicon oxide layer, and then you have your gate, your polysilicon gate, right? And if you apply a gate to source voltage, you actually create a conducting channel here. And that's how you actually have your transistor to be conducting. So there are three mechanisms which contribute to aging in transistors, and therefore in the logic gates, which are comprised of transistors. The first is hot carrier injection, or HCI. The second is bias temperature instability, BTI. And the third is oxide breakdown, or sometimes they call it dielectric breakdown, oxide or dielectric breakdown, DB or OB. Okay, and what is that? Okay. What happens here in hot carrier injection? They are energetic. They are very, very fast electrical charges flowing here. Why? Because when you apply a voltage on the gate to source, there's a channel. A lot of the free carriers in this bulk region here, they go up here, they form a conducting layer. And then there is a voltage from the drain to source, right? So example would be if you were to look at this, right? So you have a voltage here, there's a carriers form here, then you have a voltage drain to source here, right? It could be 3 volts, 5 volts and all that, because the channel is very small. The channel, this length here is now of the order of 7 nanometers, 6 nanometers, and you have a full 1.8 volt or 1.1 volt. So you can calculate the E field. The E field is very, very high. So these electrons here, from this side to this side, they are being pushed very hard. So they have a lot of electrical energy. And what happens is they start to scatter here, and then you have this mobility, saturation of the electron velocity and stuff. But what happens in the aging is that some of these electrical charges, they will actually get pushed into the oxide. Why? Because you're actually having a voltage drain to source, right? So there's a pulling force in this direction. But there's also a pulling force, attracting force in this direction, right? Because they are actually pulling all the carriers up into these conducting layers. So you can think about it, your free carriers here is actually being pushed this way, but they're also being slammed very hard against the surface here because of the gate voltage, right? So they're being pushed here and they're being pushed up here. So some of them will actually, and they're moving really, really fast in such a way that their velocity is saturated. Why? Because they are being pulled so fast by the electric field that they are knocking all the lattices and the atoms in this crystal line here, right? So some of them will just end up getting so much energy they can break through and they can embed themselves in the oxide, so they can get stuck in the oxide. So when you actually have charge getting stuck in the oxide, it's like as if you have charges that are permanently in the oxide. So what happens if you have if you actually have a positive voltage here? Let's say this is a NMOS transistor, N dope, P dope here. Sorry, if electrons, then this, let's say it's a PMOS transistor, P dope, N dope here, so you pull up electrons here, okay? So if you pull up electrons here, if you have a positive voltage here, then the electrons will be attracted up this way, right? But if some of the electrons actually get stuck here, these electrons will actually reduce the effective positive voltage here. How is that, right? Because some of these electrons will counteract, will shield the effect of the pulling effect of the positive voltage here. It will shield this channel from that, right? So it's as if this channel is seeing less of an electroactive force. So the effect of HCI is as if it's tuning the threshold voltage, right? Because it's got charges stuck here, it's as if it's tuning the threshold voltage. Okay, so HCI here is one effect. They are moving very fast, moving, and then they call hot carriers because they're moving very fast and they're slamming into the lattice and all that, and but they are not just being pulled this way, they're actually being pulled this way as well as upwards, so they're being slammed to the oxide, and they can get stuck and embedded directly into the oxide. And how can this happen? Well, you can think about it as also like the way um your SSD drive works. Your SSD drive is actually having floating charges. That means the charge is actually being embedded directly into the oxide. That's how it stores the memory, the bits, ones and zeros in a solid state drive. So it's a device specially engineered to have that. So that's possible. You can actually store and can actually embed and keep charges a long time. But this is not a specially designed gate like SSD. It's a normal transistor, and in the course of many years, imagine you're using this and you're driving current so often, there will undoubtedly be some charges that will get stuck in the oxide, and it has the effect of effectively reducing the threshold voltage, meaning that for a same VGS here, there's going to be less charges that are pulled up here. So it's like it's weakening the current, but because you don't have so many free carriers here, right? So that's how it slows things down. The second effect is bias temperature instability. And here, this happens even when there's no drain to source voltage. So if there's no drain to source voltage, there's no current flowing here. But let's say you turn on the gate. This is like a positive voltage. This is, in this case, the positive charges are here. This should be a negative voltage here. So it's the N, P, and N. So the holes can actually get embedded here. This one, the effect is just from holding the gate voltage very long, but there's no current here. Hot carrier injection, it comes from, because there's a current here, and you're actually pulling two ways, this way and this way. So you're slamming very quickly the electrons or the charges, the holes into this, right? It tends to be more here, right? Because it starts to accelerate here, then it's very fast here, then boom, it goes there. And here also is where there's a pinch off. Less charges here, so it's very dense carriers here. Bias temperature instability is more like there's just this voltage here, but there's no voltage difference here. So it's those cases where you are actually activating the gate, holding the gate at a certain voltage, but this gate is not conducting current. So the electrons or the charges are just pulled up in this way, and they can get embedded here. And it's very interesting because this bias temperature instability is a semi-reversible phenomena. So when you remove this voltage or you switch it to a different voltage, you can actually push the charge out. So it's like the charge goes in, comes out, goes in, comes out, goes in, comes out, goes in, comes out, and all that, right? So over time, some of that the free charges will get stuck here. And the effect is the same because you've got charges stuck in the oxide. It's as if you're shielding the effect of the gate voltage to create that channel. So when you apply the same gate voltage, there's less free carriers that will come out here. So that weakens the current here, slows the device down. So we see that the aging process actually is what happened is there are these two main mechanisms, HCI and BTI, that end up embedding charge in the oxide layer. Oxide layer, when you first make the device, it's got no charge in it. It's supposed to be a dielectric, no charge, but you end up pushing charge in, and this charge sort of shields the channel here from the gate voltage, so it reduces the free electrons or the free holes here, so that weakens the current available in this channel. The third is oxide breakdown. If you can apply a voltage across the gate, you can actually create defects, electrically active defects which trap charges. So it's sort of like that over time, when they are then the voltage is applied here, there is some defects, some it's like almost as if it's causing some of this oxide structure, their structure to maybe lose electrons or maybe to become damaged over time. Damage meaning that there's maybe like missing electrons, missing holes or something like that in here. Actually, there are no holes, that is a dielectric, but there are defects here that allow charge to be trapped right? And over time, there's more and more and more defects. At some point, there's so much of defects that it creates a conductive path. This is when the dielectric itself breaks down. So here you can think about this as a breakdown of the dielectric structure. What makes it a dielectric, that part of the material over time is being degraded in such a way that it can trap charges. This one is more of the fact that there's electric field that is actually moving the charges, and as part of that movement, this way, it slam the charges into the oxide. This one also, there's a very strong electric field that move the charges, pom, 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 and then it slam the charges inside. This one is more of like the effect of having an electric field here causes the material to break down. So you will have also a case of something called a soft breakdown and a hard breakdown. The soft breakdown is when you have a little bit extra charges. So it behaves very similar to these two. It starts trapping charges and then it causes the gate to delay, the transistor to delay, increase its delay. Hard breakdown is when you actually have a conducting path here. So there's like a short circuit here, and then this transistor cannot function anymore. It has failed. Okay, so in this case, aging, when you actually have the oxides, or when you actually have the charge trapped in the oxides, the transistor is still functioning. The gate is still functioning. It's only that the effective threshold voltage seems to have gone up, right? Because the gate voltage is less powerful to actually create the conducting channel. So it ends up your current is reduced, so things slow down, right? But when it's a failure case, that is the oxide breakdown, there is a direct conducting path. In this case, the charges cannot collect here. It ends up just, you apply a gate voltage here, there's current flowing through here, and then this thing doesn't really function like a transistor anymore. Okay, so this is HCI, this abbreviated BTI, and this one, some places they abbreviate TDDB, time-dependent dielectric breakdown, or here call it oxide breakdown. So there are three mechanisms. We will only be modeling the delay of HCI and BTI. Okay, so we will only, for this course, be modeling the delay of HCI and BTI, because the TDDB is a little bit more complicated. I haven't found a good way to model it yet. But for these two, there's theses that I've shared, and I'll go through some of the key points. You can actually model and quantify the delay, right? You can actually have an estimate of how much the delay will increase over time, depending on a few properties. And that's what we're going to look at, the factors that make this worse or better in different transistors. Because what we care about is actually the factors. But of course, if you can calculate a numerical number, of course, it'd be good. But I wouldn't trust the numerical number too much. It's just sort of a ballpark estimate. The key point is more of like comparing it in terms of the factors. But for your exam, for your tests, I will get you to also be able to estimate the numerical factors. So the primary process in aging is the charges actually get trapped in the oxide layer. I've repeated this a few times, but I just want to get the idea across. This increases the effective threshold of voltage. So it affects the speed of the circuit that way, right? And the key difference is this. For BTI, bias temperatures instability, it is affected by how long you hold a particular logic level. Whereas for HCI, the hot carrier injection, it is affected by the actual transition, the number of transitions that you make. Why? Because only at the transition from logic low to logic high, or logic high to logic low, you actually have current flowing. So HCI is actually dependent on having this current flowing. BTI is actually dependent on what bias value you hold here, what value of the gate. So there are two different aging mechanisms that affect the circuit, the transistor, in a different way. It really depends on how long you hold a particular logic value on that particular transistor. That would be the BTI effect. And how many transitions, logic 1 to logic 0, logic 0 to logic 1, that will be the HCI effect. What this means is that if you have a transistor, okay, so you have many transistors, but for a transistor that you switch logic 1, logic 0 very, very often, that transistor will most likely fail due to HCI, not to BTI, okay? But if you have a transistor where you hold a logic level for a very long time, then that transistor will fail under BTI and not HCI. Okay, so you have failure mechanism. Some transistors will be more vulnerable to HCI. That is those transistors that tend to have a lot of transitions. Again, hint, this would actually be your clock circuits, or basically your logic levels that have a lot of these, but there are also a few other factors. And BTI is those that actually you're holding that value for a long time. Okay, HCI, BTI, they affect NMOS and PMOS. Okay, NMOS transistor and PMOS transistor. Since HCI is dependent on the current, so NMOS and PMOS sort of equivalent lah in terms of number of transitions, right? BTI is a little bit interesting because you actually need to have this situation where there is logic here lah. Okay, so in the case of NMOS, okay, in the case of NMOS, and here, if this is logic 0, there's no channel here. Logic 0, if you're holding a logic 0 at the gate of an NMOS, you're not inducing BTI because there's no channel being created. But if you have a logic 1 here, then that NMOS actually will be suffering from BTI. So NMOS transistors that have, if you hold them at logic 1, the gate at logic 1 for a very long time, those NMOS transistors will have a tendency to age faster under BTI lah, but that would be positive bias temperature instability. Conversely, for PMOS transistor, P-type, if you put a logic 1 here, there's no channel, right? But if you put a logic 0 here, then there is a channel. The holes will actually go up here. So PMOS transistors will actually degrade if you hold the gate at logic 0 or ground for a long time. Okay, so NMOS transistors will suffer from positive bias temperature instability when they undergo logic 1 for a long time. And the PMOS transistor will undergo NBTI, negative bias temperature instability, if you hold the gate at logic 0 for a long time. Okay, let me give you an example before I go to all this. Let me give you an example for this gate here. This is an inverter, and you have NMOS and a PMOS here. Okay, let's say I actually have this inverter for some reason. It is enabling something. So I put a logic 0 here, and this is a logic 1 here. So this logic 1 is enabling maybe some circuit, and maybe for 80% of the lifespan of this gate, of maybe I'm going to run this for like maybe 5 years or something. So 80% of the time, this will be logic 0 and logic 1. If I'm holding this at the logic 0 for 80% of 5 years, there's not going to be a lot of transitions, right? Because 80% of the time it's had a logic 0. That means HCI is not a major aging mechanism for the PMOS, is not a major aging mechanism for NMOS, right? If I'm holding this at logic 0 for 80% of 5 years. Why? Because again, we saw that it is the transition, the number of transitions here on HCI that causes the aging for HCI. So if I'm holding it at a static value 0, it's not going to age. These two transistors not going to age by HCI. Logic 0 here, going to NMOS, there's no channel being created here, so there's no slamming of the free electrons into this gate. So this NMOS is not going to be aged by bias temperature instability. But because this is logic 0, this is logic 1, so there's a logic 0 here. So this is being pulled up to logic 1, right? Because this is, if this is logic 0, this is 1. So this is 1 here. So there's a logic 0 here. So there's holes being here. And this hose is always being pushed up against the edge of this channel. Why? Because of the logic 0 and the 1 here, that the difference in voltage, there's a negative voltage here. This PMOS transistor will suffer from severe NBTI, negative bias temperature instability. So if I give you the way this transistor is, I say if this is going to be at logic 0 for a long time, for most of the time, 80% of the time over 5 years, then the primary aging mechanism of this NOT gate is NBTI will degrade the PMOS speed. Okay, NBTI will degrade the PMOS speed. If I change this to be held at logic 1, let's say for some other part, this NOT gate I use elsewhere, and this is held at logic 1. So it'll be logic 0 here. The PMOS is not degraded because it's logic 1, there's no channel here, but logic 1 here, there's going to be a positive voltage here. So this channel will be there, but there's not going to be current because it's held for 80% of the time. So in that case, my primary aging mechanism will be PBTI, positive bias temperature instability, affecting the NMOS. So it's going to degrade the speed of the NMOS. And if I were to tell you, I use this inverter in a ring oscillator, right? A ring oscillator, I think we talked about it very briefly some time ago. Is basically an oscillator of, I think the last session is odd number of NOT gates. You put them in feedback, so they start generating a clock. Plus, minus, plus. I goes logic 1, logic 0, logic 1, logic 0. So if I were to use this in a ring oscillator, then actually I have and if I tell you that the duty cycle is 50%, that means half the time I'm spending in logic 1, half the time it's logic 0, then the primary mechanism probably will either be HCI. HCIs will be a dominant mechanism because you have a lot of transitions, 1, 0, 1, 0, 1, 0, 1, 0. So both the PMOS and NMOS will be affected by HCI, but they will also be equally affected by NBTI and PBTI because you're having half the time at logic 0, half the time at logic 1. And if I will tell you that this 1, 0, 1, 0, 1, 0, that is a duty cycle, let's say is a 70% duty cycle. That means 70% of the clock period will be at logic 1 and 30% of the clock period will be at logic 0. Then the PBTI will be worse than the MBTI because you have more time of this gate being spent in logic 1. So it's going to age this faster and less time of the gates being spent in logic 0, which will age this. So you can actually say the MBTI will be worse. Okay. So with this example, I hope you can understand how looking at the activity of the gate, whether it's being held logic 1, logic 0, how long it's being held, as well as whether it's transitions or being held at a main value, that can hint to you what is the sort of dominant aging effect. Okay, so that's the first step for you to understand. Okay, that you can actually tell it apart by its activity or by its logic level. And again, BTI, like I said, is a partially reversible, right? It's partially reversible, and that's indicated by this. So we can actually represent the effect of aging due to bias temperature instability by a change in threshold voltage. So threshold voltage goes up, then comes down, goes up, then comes down. Why? Because over time, like you switch it on and off, on and off, on and off, on and off, right? If you hold it at the logic 0, maybe it's quite bad. Then you switch it to logic 1, then it reverses some of the charge escape. Then you hold it at logic 0, it goes up and down, up and down. But over time, there's a slow drift, a longer term drift. This is the delay due to the aging. Okay, so this just to let you understand this. Okay, so again, why are we talking about change in VTH? Why are we talking about change in current? Well, at the end of the day, we are saying that the gate slows down, right? The transistor slows down, then that slows down the gate, right? But we can model the slowdown in transistor speed like a change in VTH, like because basically from the process variations, you understand that if you change the drive current, you actually, if you reduce the drive current, you slow it down. You increase the drive current, you enhance the speed. So in this case, increasing the VTH will actually reduce the drive current. So you can actually model the increased delay by a change in the VTH. And this delta VTH is a mean value, a change in the mean value of this of the transistor. So it seems to be like as if you are changing the delay. And we also saw qualitatively, if there are charges that are trapped in the oxide, is as if we are reducing the effective VTH. Have we actually reduced the VTH? No, the same voltage will actually give the current, the channel here, right, with a certain number of charges. But because there are some charges stuck in the oxide, even you apply a voltage across here, the effective voltage seen in this channel is less. The effective voltage difference. That's why it seems to be as if the threshold voltage is changed. It's not actually changed, it's just that it looks like it's changed, and we can model that as a delta VTH. It's just the way we model it. Okay. Right. So two effects. I think I'm covering NBTI because for a long time, PMOS appears to be worse than NMOS, but nowadays we're not quite so sure anymore. But anyway, I cover one. The numbers are sort of similar. And I think the key point actually I wanted to show you in terms of modeling is here. The mean change in VTH is modeled by this equation. The mean change in VTH modeled by this equation. A is some kind of constant is dependent on the exponent of some value, some activation energy EA, Boltzmann constant, and temperature. That means it's actually dependent on temperature. So if you're operating the circuit at a higher temperature, you make the aging effect worse. And it's also dependent on the voltage. Okay, in this case, BTI is dependent on the voltage, right? Because again, BTI, if you have a larger voltage difference, you're going to push the charges harder into the oxide. So it's actually dependent on the voltage, and it's dependent on the duration on time that you are actually applying this stress, +1 plus the capacitance divided by the width. That means if you have a wider gate, a wider transistor, the effect of the aging is not as bad. Okay, so this BTI is a little bit well modeled. You can look at the mean change in threshold voltage due to aging, right? Because it's going to be a function of time, how long you're stressing this, and the variance of that change in threshold voltage. Again, the effective change in threshold, we're modeling this as a change in threshold voltage. This is the mean shift, the mean increase in the threshold voltage that leads to a greater delay. This is the standard deviation. It's going to be proportional to the square root of W and L. This means that the smaller your process technology, let's say going from 180 nanometers to 90 nanometers to 60 to 10 nanometers, the worse your aging is going to become, right? Because it's inversely proportional to the square root of L. If you're using smaller transistors, the width is smaller, the worse your aging is going to become. That means what I'm meaning to say is you can actually say that if I actually have two transistors or two logic gates that were actually using exactly the same effect, the same duration in stress, the size 2, the 2x size standard cell is going to have not so bad the aging as compared to VTH. How much worse is proportional to 1 over W. Okay, and then the variance is proportional to 1 over square root of W. So you can get the factor of how much worse one transistor is. So these equations are nice because they actually tell you how to compare logic gates in a digital path. And you can sort of use this as a rule of thumb to say, this gate is going to age worse than this gate is going to age worse than this gate, this particular transistor is going to be the worst case and all that. And again, where would you take to apply this? Well, if you're actually worried about again, the key point here is that over time, your whole circuit, the delay actually goes up. And what you worry about is the delay goes up to a point it breaks the specification. That means then in that case, you're actually not able to run this as fast as you can. That means the circuit will still work, but you have to slow down the clock. Or if you're still running at that clock, which most circuits, the clock will just be about the same, then the circuit will start to have timing violations. That's what will happen. So so this so in that case, what we're looking for is most likely we will apply this analysis on the critical path, because any change in timing of the critical path is the one that's going to break the circuit first. And of course, because you know about process variations, you also know that it's better to not just apply this on the critical path, but also apply this analysis on the near critical path. It means this type of analysis on aging is useful not to apply to the whole circuit, right? Because all of them the whole circuit will age and all that, but you're actually mostly putting your attention on, again, the critical path and the near critical path, because the effect of increasing the delay of these two paths is more catastrophic than in other parts of the circuit. Because if it's not a critical path, it's not near critical path, even if you age it, it's fine, if you age it at the point where it gets as slow as a critical path, then that's where you start to worry. But your critical path is going to age first before those other circuits, that kind of things. So this type of analysis, again, is quite useful if you apply on the critical path and near critical path to see what is the risk of timing failures and what is the sensitivity of your circuit to aging. And if you care about aging, if you are looking at wanting to use this type of circuits for long duration in time, 5 years, 10 years, then, or you want high reliability, then you might need to do some analysis here so you can have all the qualitative factors that help you compare which one is more sensitive, and you can also have some guidelines how to sort of estimate this to within certain ballpark. Okay, so that's the whole point of actually getting you to do the BTI and the HCI sort of analysis, that you look at the path into a logic circuit. At this point for this semester, I'm just going to get you to do analysis on individual gates. But I can test you on NOT gate, I can test you on NOR gate, NAND gate, XOR, anything, right? So for you to just see, A, do you understand how to apply these factors? B, do you understand what causes this stress time? That will be how long, if for HCI, how much percentage you're spending on the transitions. For BTI, how long proportion you're spending on the logic level that's causing the stress. And the logic level that's causing the stress is the logic level that is creating the channel, the conductive channel in the device. So BTI is a static effect that if you're holding this gate static for a long time, that's when it happens. But even if you're switching it, the percentage of time you're spending at logic 1 or logic 0 is going to help, is going to really contribute. HCI is just how much time are you actually just pumping current through this transistor. And of course, if you that means that tends to happen when you are actually transitioning from logic 0 to logic 1, logic 1 to logic 0. So in very, very quiet circuits, inactive circuits, HCI is not an issue. HCI is an issue in very active circuits. And BTI actually is always an issue because as long as you're holding that logic level, you will suffer from it. Okay, so NBTI in a way is sort of something that you look for first. Okay, where do you get these values here? That's an interesting point. You can dive into that that thesis that is in that I've shared with you in ULearn X is actually detailed out in chapter 3, aging effects. You're looking at okay, you're looking at equation 3.7. So you have A, E, A, K, B, and C, they are constants, time dependence n. So this paper by Massey in 2004 report the value of n, which is the power of T stress here. This value of n is between 0.15 to 0.3, and VTH increases monotonically with time, and it also gives the value of EA between 0.1 to 0.36 electron volts. So you can read this here, check up. You just pick some value, you just justify it. I'm not going to be too fussy which value you pick, but I just want you to kind of look up these theses and kind of read through a little bit the reference paper, then you pick your favorite value, and you give some justification why you pick those values within this experimental range. And then I think for A and for C, you can just assume something, or you can just say it's proportional. You just let your VTH be some portion of A is fine. Or you can read up and you can see if there's any value that's suggested. But these probably are some experimentally determined values. But if I ask you to analyze, then I expect you to solve these parts lah. Like these parts here, you should be able to solve, especially the temperature. The VGS, you should be able to, because VGS usually is very close to VDD, lah, right? Because this is the value of the what you will put in the gate, right? This is the value of what you will put in the gate, right? Because if you look here, you're applying logic 1 or logic 0 at the gate, right? It's just if it's logic 0, this to this is negative 5 volts. This to this is positive 5 volts, is logic 1 lah. So VGS is close to VDD lah. So that's where the VDD effect comes in lah. The higher the VDD, the worse the VTH. The lower the VDD, the less the shift in delay. T-stress, so you have to understand how to calculate it, how to estimate it. And T-stress is basically nothing else but the probability or the percentage of time that is under stress times the total lifetime of this circuit, how long you're operating. So T life will be, I give you 5 years, 10 years, that's a number of years. P stress will be what is the proportion of that time where it's under stress. Okay, what is the proportion of that time where it's under stress? So if it's NBTI or BTI, of course, it's easier. If it's NBTI, of course, it's easier to assume, right? Because it's always going to be a logic 1 or logic 0, right? So like, yeah, you just have to know whether it's 50-50. 50, if it's 50-50 duty cycle, or 50% of the time is in logic 1, logic 0, then it's just half of the stress to time duration. If the logic or duty cycle is a bit different, then you just have to take a percentage of that. The HCI is a little bit more difficult to calculate because the time that you are in stress is just the time of that transition over the whole thing. But here's where you can actually look at some data on what is the slew rate. Slew rate will be like how fast are you actually going from logic 0 to logic 1, logic 1 to logic 0. That's typically like 5%, 10% of the clock period, right? So you can actually say that in one clock period, if you take the slew rate to be 10%, so 20% of the time is of the clock period is for transition per clock period. So the worst case for the clock would actually be 20% of the probability if you're assuming a 10% slew rate, okay, of the clock duration. So you can make those arguments that way, and then you can sort of estimate how often the transitions happen, the activity factor. So if there is more often transitions, then you will scale that approximately. But this is just to show you how to actually estimate that that time of stress, this T stress. And then this is the power of B, this power of N, you're taking the power of this. And then you can check that messy paper how to get that estimate, right? So once you can calculate delta VTH, you should be able to apply this delta VTH to calculate what is the delta ion. And once you get the delta ion, you should be able to say how much longer is the delay, like how much additional delay time it is. And as I mentioned, this delta VTH is a mean, a change in the mean of the effective VTH. So it's going to affect the delay in the mean way. And of course, the standard deviation is going to be proportional to W and L. Right. And this type of equation is useful to, well, you can do it quantitatively. I'm not really care so much about what values to select here. Just make it realistic, look up the messy paper, put down something. But I need to be able to see that you can actually take this all the way, DVTH, to convert it all the way to delay, how much more delay. And I also may want to ask you to evaluate this comparing different circuit, let's say different transistor. So I have a larger transistor, smaller transistor, different level of stress duration, different VGS. Would you be able to tell me which one the BTI is worse by maybe a factor of 10, a factor of 100, or, how much worse is it? That kind of thing, right? So these type of equations are useful for those kind of comparative analysis as well. Okay. Now, HCI is a little bit more challenging. And remember, it is basically whenever you are driving current through the gate. So it's only on the transitions. And HCI then changes both the effective threshold voltage, because remember the charge is being embedded in the oxide, and also it changes the mobility of the transistor. right? It's actually changing the mobility mu of the transistor. Why? Because again, the charges are being trapped here. Okay, when the charges are trapped here, there is when you apply a voltage here, there's less electric field that can actually pull the charges up. So you look at a change in threshold voltage. But also when you're actually moving here, you suddenly will have additional charge here that is kind of deflecting, like disturbing the motion of the electrons or the holes here, right? So that's that. So these additional charges in the oxide not just is reducing the number of free carriers here, they're also interfering with the flow here, because it's as if you've got a bit more attractive forces that will kind of distract the charges from flowing here. So they get effectively a little bit slowed down. So there are two ways where HCI is actually changing. It's actually changing mu and actually changing VTH. So you can't actually directly kind of model the effect by change in VTH or change in mu. So how it's usually modeled is a change in the on current, the change in the on current. So change in the on current is a little bit tricky because yeah, it's not so straightforward to uh, convert this to speed, right? But you can you can make this a proportional argument. So you can still calculate all of this, except that VDS is this is now a function of VDS, not VGS. So VGS for MBTI, because it's basically the gate to source voltage here, how strong you're pulling. For HCI is actually VDS, the voltage across here, how strong you're pulling the charges here. For BTI is how strong you're pulling the charges here, VGS. So they are different voltages, right? So here, if you look at the NOT gate, VDS also is roughly about 5 volt. But where you start to see a difference is when you actually have a chain of series gates. Let's say you have a NAND gate or NOR gate. When you have two gates in series, the VDS is going to be less because the gates are probably good. The transistors are probably going to be same size. So roughly it's going to be half of VDD if you've got two in series. If you've got three in series, it's going to be 1/3 of VDD. So NAND and NOR gates will have slightly better HCI than NOT gates because the VDS will be reduced by the number of gates in series. The T-stress is the same, and here is dependent on the channel length, whereas previously is this PTI is inversely proportional to width, not so much affected by channel length. Okay, so slightly different factors that affect it, and here again, you're modeling the effect of HCI as a change in the mean value of the on current. And usually how this is modeled is actually modeled as both a change in the on current, there's an interfering current source and a change in the threshold voltage. But I can make life a little bit simpler. I'm going to make life a little bit simpler. If I ask you this question, I'll just tell you that model this HCI as a change in VTH. So first you calculate the change in ion, then you figure out this change in ion, what is the equivalent change in VTH, something like that. Then you can then figure out what is the delay, or you can actually directly relate this ion to delay, just the way that it's done in the process variation. That either or is fine. Okay, and again, the stress time, again, as we discussed, is you have to estimate the proportion of time that the transitions will take, which is both that slew rate, how fast, what is the percentage of time in one clock cycle that that you actually have this current moving. That's roughly the slew rate. And then how often is this triggering transitioning per clock cycle. You can actually estimate it that way. Okay, so there are two ways to do it. And why I'm actually showing you this DION and DVTH, because at the end of the day, the change in delay, right? You have, this is the delay. This is the delay after aging. This is the delay when the chip is just freshly made. It's actually, there's going to be how the delay is changed as a function of VTH times the actual change in the effective VTH, and then how the delay is changed as a function of ion times the actual change in ion. So this one is probably the effect from BTI, and this is the effect from ion. And here there is some derivation in the book that actually shows you this parameter. You can actually calculate it in terms of alpha, delay, VTH, and VDD. So if you can model this delta ion as a delta VTH, basically I'm giving you a way to estimate this entirely by equation. You just use this part of the equation. You can estimate what is the actual fresh delay. Then you have the delta delay over VTH from this closed source expression here. Then you can calculate the delta VTH this way. You calculate the delta ion here, and then you translate this into a delta VTH. If I give you the assumption that you don't need to model it as a change in mobility, you can just model it as a change in VTH. Then you can plug the value in. You can actually give me the actual numerical value of the H delay. Okay, that is why I'm showing you these equations, that you can use them in your calculation. And this is showing you that the delay is going to be linearly change as a function of VTH, any change in effective VTH. Okay, and then this is just telling you that it's just a function of the effective voltage, the effective temperature, the time over which is stressed. So change in VTH is actually dependent on channel length. Change in drive current is actually dependent on channel on the transistor width. That means HCI effect will differ greatly between size 1, size 2, size 3, size 4 standard cells, whereas the BTI effects will get worse as you move from process type, 180 nanometers to 90 nanometers to 10 nanometers and so on. Okay. All right, and then here, this is just, you won't be tested on this, but this is just to show you some working from the thesis again, where they actually can look at combining the effect. Let's say you're able to model that your circuit is operating between 125 to 150 degrees for a certain percentage of its lifespan, and then within this range for another certain percentage, and within this temperature range for another percentage. So this is where sometimes you have your circuit shut down, for example. So if it's shut down, it's probably going to be around this temperature, 27 degrees, 25 degrees. Then if it's actually idling certain steady state value, maybe it'll be somewhere in this range. And then this range is when it's actually actively switching. So if you have actually the activity profile and you can actually match it to the temperature, you can get more precise estimates of the effect of aging by ratioing the duration in which it is actually at this temperature. Because again, remember the delta VTH, the drift in VTH depends on the duration at which it's stressed as well as the temperature. So you can do a ratioing of maybe 20% of the time of the stress is at a higher temperature, maybe 60% is at a different temperature, mid temperature, and then the other 20% is at a low temperature. So there'll be different during these different periods of temperature operation, they'll contribute different amount of aging delay. So you can estimate the whole total aging delay. This, again, I repeat, is not coming up for your exam, not coming up for your test, but I just share with you in case you want a more accurate way of modeling for your own workplace in that case. Okay, so I'm going to take a brief pause at this moment to see, do you understand what I've shared with you about aging? Again, the recap, I'll recap at the end of this, but I'll just pause to take any questions at the moment. Do you understand and do you follow what I'm requesting from you? I want you to be able to qualitatively evaluate. Let's say I give you a logic gate, or I give you a logic path, which you have to convert it into its constituent gates. Then I'm going to ask you, you analyze the effect of aging. So you have to look at a few things. First, you have to look at what type of activity is at that gate, whether it is holding steady values or its transitions, right? Because different aging effect will be dominant depending on that. And different effect will be dominant on PMOS versus NMOS. So you should be able to say something of that sort. And you also should know that, again, that different effects will be dependent again on channel length, channel width, and things like that. You should be able to understand and say that. Second, I would need you to be able to estimate that. Like I said, you can estimate the NBTI by a change in BTH. You can look up all these constants in the thesis. There's a paper by Massey in 2004. Go read it, and then learn how to plug in those values, get some number here, and then the ion, and then you can reference this equation. And I will give you, if I ask you to do something on HCI, I will tell you, please reference this d delta ion is just model it as a change in BTH. So you use this equation to calculate delta ion, then you convert this delta ion into an equivalent delta VTH. Then you can actually just plug in using just this. So you have one d delta dVTH due to NBTI plus another d delta dVTH due to HCI. So you have two of these terms, and then you times by d fresh, and then you have this here. Okay, then you can get the aging value, the delay due to aging. Okay, just a quick pause to see if there are any questions, if you have comprehended this. Yeah, so this will be coming up for tests. It will be coming up for final exam. It will be one question on this.
Evening, doctor. So
Good evening, Astri.
for this aging topic, you're going to be asked in test number 2, is it? Isn't it? And also
Yes, it's
final.
going to be one of the question in test number 2, and it also will be one of the question in final exam. So final exam, there are 4 questions. Test 1 got 2 questions, test 2 got 2 questions, but test 1 and test 2 will be exactly mirroring final exam. The way of asking the question in test 1 and test 2 will be exactly the same in final exam. The only thing is I will change the circuit, I will change the number, I will change some of the questions a bit, but the style will exactly be the same. So you study the test 1 and test 2. Also, it's a good preparation for final exam. But of course, it's not going to come out the same question. It's going to be something else. So maybe I may ask you one effect in test 2 and then another effect in final exam, something like that. But what basically is I need you to be able to qualitatively explain. Let's say you look at either a gate, a standard cell like that. It could be a NOR gate, a NAND gate, a NOT gate, XOR gate, any of the standard cell gates, or I could actually give you a path, right? A simple set of logic gates, and you have to translate it and ask you, analyze this, tell me, which is which part of the circuit is going to be most prone to aging. Then you have to start pulling all these things together. You have to look at, how you can compare whether it's transitions or it's logic levels. Again, it's not every logic level, right? It's logic 0 will affect the PMOS, logic 1 will affect the NMOS. You have to be able to see the circuit. Is it mostly going to be a logic 1 or logic 0? Or it's going to be roughly half. And then how many transitions are there? Is it going to be transitioning very fast or very slow? Then use that to argue which is the dominant aging effects. Then you can also look at things like the temperature, the voltage, the channel length or the channel width to argue, is this going to be, which aging is going to be dominant, or both are going to be present or something like that. And then second, I probably want you to calculate and you tell me how much worse the delay is going to be under that aging effect after 5 years or after 8 years or after 2 months, something like that. Okay, so you should be able to calculate the change in threshold voltage, the change in ion, ion, then you convert that into delay, change in delay. This is the delay of the fresh chip plus this part here, and the delta dVTH is given down here in this derivation here. I'll share these slides. Okay, then this delta VTH, as I shared, you can calculate this under NBTI. For HCI, is a little bit more work. You first have to calculate delta ion. Then you reference back, there was an equation that gives you a sensitivity analysis from the process variation, the ion as a function of VTH. You can relate that. Then you get the delta VTH corresponding to this delta ion. Then you can actually plug in here to this. Okay. Did that help, Asri?
Yes, brother. Thank you.
Okay, never mind. You try it out. You try it out. Maybe the simple case would be you try working it out for maybe you pick I've got the NOT gate, the simplest one here. You can also try working out for another few other gates, and then if any questions we can discuss again in the next session lah. As I mentioned earlier today, this is not going to be our last session because I definitely will need to have another discussion after the tests. I don't know if I will combine them into two sessions. I do one session or I will do two sessions. Most likely, it looks like I will have to do two sessions because I'm expecting a lot of questions for the test. So tonight, I'm not going to be talking too much because just get you started on the aging so you can prepare for your test 2. Then you focus on your test 1 and test 2. And then after that, we're going to have another 1 or 2 sessions to review all the test answers. So that will give you a good preparation for your exam lah. But it's a bit unfortunate that your PBL2 and is being lumped quite close to all of that lah. But you'll have to manage that lah because the PBL I've given quite some time already. The tutorial 2 we'll cover shortly. I pushed that to 3rd December because the tutorial actually is not really important for final exam or the test. It's more of like just deepening your understanding. I'm still going to give you 5% for that. It's not that much, but it's not that difficult to get it done. Okay, I'll just walk through it. It's just that I think I was missing the analog file. That's why a bit difficult for you to work on it. Yeah. Okay. So are there more questions on the aging part? Or can I go on to talk about tutorial 2 a little bit?
Can proceed to tutorial 2.
Okay, so the others, if you have some question, you just interrupt me. Yeah? Okay, I just go back to tutorial 2. Okay, first I want to talk about the rubrics of the tutorial, how I will actually grade it. For tutorial 1, there are 3 questions. Show briefly that you have successfully executed this. The second is identify and describe the outputs of static timing analysis. The third, pick any logic path and locate its user diagram, extract the wire capacitance and the wire routed path. So normally the rubric, there'll be 1 mark to 5 marks. 5, of course, is A. 4 is like 80% is A minus lah. 3 is 60% is like a B. This is passing mark lah. Typically, you want to be this 3 and above because if you're 3 and above, most likely you will pass with a B thereabouts lah, and your CGPA will be maintained. But you want to try to hit 4 and above as much as possible lah. But if you have a mixture of 3 and 4s, you're still going to be okay lah. I would actually say 3 is considered like a passing mark. Although 40% is a passing mark, you actually need to have CGPA B and above, 3.0 and above lah. So you should actually be aiming for mixture of 3s and 4. Okay, how I'm going to grade tutorial 1. Okay, if you just produce evidence of completing the steps lah, maybe you give me a printout or something, there's 3 marks. But if you demonstrate successful execution outputs, you actually show me that, okay, these are the outputs of the files and all that, because what I want to, my criteria here is I actually want you to execute the tutorials lah, and to understand, right? But if you just click and write the keywords, it means you haven't gotten deep into understand it. So I'm just giving you 3 out of 5 marks. And if you actually organize the outputs, you actually explain this is what's the output, this is what's all the steps and stuff like that. What is the meaning of each step? What's the purpose? That's going to be a 5. Okay. And for static timing analysis, again, if you just produce and you show the outputs, let's say you just open the STA, you just show it to me. You don't tell me what is it. You just put it there. That will be a 3. But if you start telling me things like, okay, this STA, I have, this is the max delay and all that. You mentioned it briefly, right? But you not really tell me for which circuit, you don't highlight which part of the circuit, you just kind of like defining, but you with reference to like the printout and all that, that's a 4. But if you take some pains, you actually say, okay, this is static timing analysis, this is the path, this is the input, this is the output, here's the location of the path, this is the components of the static timing analysis. It's got the slack, and this is what the slack means. It's got the skew, this is what the skew means and all that. That's a 5. So similar to the extract the wire cap, if you were just to show me like a file, right? And then you just tell me you can get that is a file, and then you just let me read that you can actually pull out, but you don't actually tell me this is where I find the capacitance, what's the capacitance value, where is it, then that's a tree. If you were to actually just pull out it's a file, then you kind of tell me, okay, more or less, this is the capacitance value. I can pull it out, and it's for some path or some circuit or some wire, okay. But if you were to actually be a bit more creative, you write some code, or you actually find a way to extract that wire capacitance, and it's very clear which that you can do this in any wire, that's a 5. Okay. Because here's going for adapting it. The last one is actually more like wanting you to really understand it. So this is how I'm going to be grading tutorial 1. I'm midway grading tutorial 1, and I was thinking I might actually give you all the chance to resubmit if you feel that you're not happy with your grade lah. So maybe by next week I should be able to give you your marks broken down, and then the 5 marks will be averaged across these 3 lah. I might, if there's demand, I might just allow you to resubmit lah. But the whole point of this is to get you to understand in detail, a bit more detail. But again, the tutorials are not related to exam, they're not related to test. But of course, if you understand question 1 a lot, then of that will help you for your test and your exam, because there's going to be one question on the design, the design flow anyway. Okay, tutorial 2, more relevant to you. There are 4 parts to it. Again, I will grade you 5 marks for each part, and then I will just take the average of this, divide by 4. Sum everything, divide by 4. So the first is analog MOSFET, draw PMOS and NMOSFET and connect them as an inverter. Okay, here what was missing was I actually did not give you, I had thought about it, but somehow when I was updating it, I didn't actually give you the analog file. So that's why I'm replacing I've given you a link to the file. I'm pending to do a little bit more cleanup. But if you want to go ahead and get started on it, it's okay. But what I've actually done is I've extended the deadline up to 3rd December 2023. So the thinking is that this week, it's much better if you prepare for your test 1. We go through all the lessons online, our discussion, make sure you know how to calculate, make sure you know in detail the flow of the design flow. Please open the Google Colab, the Silicon Initiative, Google Silicon Initiative. Please take a look at this part here. There's the libraries, like say the 130 nanometer, 180 nanometer one. There is the there is the documentation for it. Please take a look at that. We had covered that in the previous recorded session. The documentation here, at least one of these. Please go in, look at digital libraries, look at the physical verification, just browse through all these, read it a little bit, all these parts here. What is physical verification, IP, macros, just read, browse through it, get sort of the main idea. Look at that. And understand very well the process flow, because those are going to be coming up in your tests and in your exam. Okay. But here what happened is I've added something else. This is the digital, there's both the digital code and an analog code. So the analog code, I've sent you the link to the file here, the Jupyter notebook, but I haven't, I'm pending to actually improve it onto the Docker. This one here is just I'm giving you the raw, you can execute in Colab, but I haven't tested it out on the Docker yet. But anyway, what this notebook is doing, it's actually this analog inverter part here. So if you open this and you execute it, you will see this one is installing the libraries. That's the part that I wanted to clean up so that it's easier for you to run on Docker, but you can actually just run it on Colab as well. This is just installing all of that. But at this point here, this part here is a script to actually draw a MOSFET with a tool called Magic. So it's actually giving you the size of the polysilicon, the size of the gate, the size of the... So this is your transistor here. So you have the gate here, you have the drain, you have the source here. So this is actually showing you how to draw the MOSFET. The top part here is actually drawing the MOSFET here. This code here is drawing the MOSFET, this script using Magic. And then it is calling up this library, GDSK, but it's reading the drawing. The GDS file is the drawing. Okay, it's showing you the drawing. And it's taking that MOSFET drawing and is simulating it with PSpice here, a PySpice here. Okay, it's able to, so this is like a backward. You start from a drawing and then you simulate the performance of it in a circuit. So you can actually go study this. This is actually a simple circuit, how to draw it. It's actually looking at the switching property of the MOSFET here. Okay, single MOSFET. Now the tutorial is just a slight difference. So that one was just a MOSFET. I think that was an N MOSFET. I want you to draw a PMOS and an NMOS, and I want you to connect them up together like an inverter. That's what question one is. It's just given you have this example, okay, you can actually draw this. This is a N MOSFET. I want you to create a P MOSFET together with the N MOSFET, and then I want you to connect up the gate and the drain and the source in such a way that it forms an inverter, simple inverter. And then I'm going to get you to simulate that inverter. Okay? That's what I'm asking you to do, right? So here, get that, and then simulate that inverter. Okay. Here I'm asking you to draw it out, right? Then I'm asking you to basically figure out for 130 nanometer, maybe asking you to actually look a little bit in the PySpice. How do you get the capacitance at this part here? VDS, the junction capacitance, the gate capacitance. How do you measure that or extract that out of the PySpice module? Right, so you go to look for PSpice, you just look up how to pull out the capacitance, and then here the IV characteristic. Basically, I sort of want you to basically plot maybe IV was wrong but if you can do it by IV, that means you actually plot in PSpice the IV characteristic, and then you can look at, because IV, when you have IV, you can actually estimate the effective resistance. So the whole point of this is actually to ask you to estimate the effective resistance of the MOSFET. So I'm actually asking you to simulate this resistance here. So when there's current flowing this through here, this MOSFET is acting like a resistor. I'm asking you to simulate it by plotting the IV characteristic of this PMOS, by plotting the IV characteristic NMOS. So you know that resistance is dV over di, right? This is resistance. So if you got a graph, I versus V, you take the slope of this graph is 1 over R. So then you can actually estimate what is the R of this. And where we're going with this is because you understand that the delay model that we have is actually an RC time constant, right? The C is basically the load capacitance at the output. How you get the timing is you see what is the effective R of the PMOS. So you get the RC, or the effective R of the NMOS, you get the RC. So now you can see where I'm taking you with this simulation. Actually, going back to fundamentals basic, if you got the library model here, the lib.spice file, you actually can simulate the IV characteristic of the MOSFET. You can estimate the R value. You And then you can actually estimate here in number 2, the gate capacitance and the junction capacitance. Gate capacitance is here. So it's basically you are using to estimate what is the capacitance at this level. Junction capacitance is here. So I'm getting you to be able to extract the capacitance here and the capacitance here. So if you know how to do that, the whole idea is for you to understand that from this Liberty file, you can actually estimate R, you can estimate the capacitance at the gate here, you can estimate the capacitance at the gate here. So if you're given that model, straight away you can extract the R and C parameters from your basic transistors, your standard cells, without looking at the data sheet. You can actually do that from a circuit parameter, and then you can start estimating the RC delay. That's where what the whole point of tutorial 2 is trying to show you that you actually can develop that knowledge. It's not very difficult because the models are all there. You can actually get the R and the C from the analog side. This is getting the C, this is getting the R. So with the RC, you can be able to estimate the delay of the MOSFET, and therefore from that, when you start putting them together in different logic gate configuration, you can estimate their delay. And question 4 is using the digital version of that. Okay, so question 4, in question 4, basically the RTL code is synthesizing single inverter. That's the RTL code. What I'm asking you to do is to build what we call a fan out of 4 inverters. I'm asking you to build using the RTL and the digital version of it. Connect a circuit like this. You have an input like this. You get some kind of output like this. Estimate what is, you can simulate what is the delay here. Okay, and this T delay here is called fan out of 4 delay. And this is for logical effort. So this is the second way for you to estimate delay. So the whole point of this tutorial question is to show you that from the Liberty file models, you have the analog way of actually estimating delay. That is, you get the capacitance from 2, and you get the equivalent resistance from number 3. Or you have the digital way, which is the logical effort. You can estimate the fan out of 4 for inverters, and then you can use logical effort to basically use that fan out of 4 delay with logical effort for NAND gate, for NAND gate, NOR gate, and all those other gates. So the whole point of this tutorial is to show you that given the Liberty file model, you can use these tools to basically, from simulation, basically extract out these parameters from the Liberty file model from the fab. All right, and that gives you way more flexibility in simulation and hand calculation. You can actually use these realistic models, right? So that's the purpose of tutorial 2. So you have all that is necessary. It's just that the analog code here, it actually has, as you were seeing in just now, so scrolling up, it's quite a lot of setup here. Before we come to this part here, there's all this part of actually setting up the tool and all that. So what I'm trying to do is, just like the digital version, I want to actually just set all this up in the Docker so that you can just run this. But if you want, you can just run this on Google Colab, so it will work. And you can actually do the edits. You can create a new file and you can actually edit it here. And you can actually solve the problem with Google Colab. It's not going to be too difficult. But for your convenience, I will actually work on and create another Docker for this. That's why I've shifted it to 3rd December. And again, as I said, it's not essential to your test 1, test 2, or PBL 2, or your final exam. But there's certain things I wanted you to learn and to show you. And that's why I'm just giving that 5% for that. And it's basically to show you 2 different ways to estimate some basic delay parameters, which you can then use in your hand calculation estimates. You can use the analog version of getting the R, the C, and the R. So you got the RC time delay. So you know the time constant RC ln 2 from the textbook. So you can actually estimate that. Or you can do the digital way, which is, there's an example here. It's just 1 inverter, but you have to connect that inverter to a load of 4 inverters. And then you are actually looking at the delay of this inverter, not this inverter. These 4 inverters are actually the load of this. Right, and that is called the fan out 4 delay. And then you can use that fan out for delay as the basic unit for your logical effort calculation for delays, right? So that is the whole point of this experiment. Okay. All right. Any questions from people at this stage?
Doctor, I have a question.
Sure.
These tutorials and also the test. Okay. Primarily on the tutorial, because Docker is not running on my machines. I've tried to troubleshoot and do some of those. But it didn't work. And until now, Docker is not actually working. So is it enough to just use the Google Colab for?
Yeah.
All of
Firdaus,
this?
I'm totally fine if you use Google Colab and you solve the problem. This is 100% acceptable. The reason I created Docker is because some people, they can't wait for the Google Colab, or they actually want this to run their machine and things like that. You don't have to do your Docker. You just need to solve it, right? So if you get it done on the Google Lab, show me the Google Lab. That's perfectly fine. No penalty, nothing, right? In fact, Google Colab's the fastest way to get it done. It's just sometimes you may need to edit certain things, so it gets a little bit of a pain. But if you can get it done on Google Colab, please, by all means, please don't spend time debugging the Docker, because most likely what's happening is maybe the setup, maybe either your Docker wasn't installed properly, or there was some path that has to be set. I posted in the WhatsApp, but maybe you missed that. So that has to be set. But the Docker was more of a convenience because some people didn't really want to use the collab.
Yeah. I see Docker is more convenient. I use the text that you've sent in the WhatsApp group, but the Docker is still at the starting up phase. And then when I check, it said something like the distributable is missing in the machines and something like that. But I've downloaded that, but still it's not working for the Docker. I mean, on
Okay.
my.
Are you okay using Colab? If you're okay, Firdaus, then I would recommend using Colab, because at this stage, I think debugging the Docker is going to be a pain.
Yeah.
It's going to take a lot of time, actually. Yeah.
Yes. I've tried using Anaconda and then run that Jupyter, so that's working.
That's fine. If you use Anaconda and Jupyter on your local notebook, whatever method, as long as you get it running on your somewhere, it's perfectly fine. I don't tie you to a particular system, because you're using the same open lane library anyway. It's just the underlying execution. But if you are very well versed in Anaconda and stuff, and you got it running, great, power to you. It's good. Just complete the tutorial. I don't really need you to be in Docker or anything like that. Yeah.
Okay, Doctor. Right. Thanks, Doctor.
Sure. Thanks.
Doctor, I
Yes,
have one
Asri.
question.
Sure.
I tried to run the line in the Google Colab for the tutorial number 2, but for the drawing, I think drawing using magic.
Yes.
The part that drawing using magic.
Yes.
Yeah. I think this one can. If you try to run this, it can run, but I think this part is something missing. Something I don't know. But when I try to run using Docker, it can run. It can complete the process. But when I try using the Google Colab, I think draw. Is there something missing file or?
Okay. Asri, at this point, I can just give you my guess lah. If you try running on Google Colab, you need to actually execute all of this. And you actually need to open it on this Chip Alliance site lah. What I tried to do is I tried to copy this into my own local and run it on Google. It just doesn't work because some of the virtual machine that's running it doesn't have certain paths. So it was such a pain to debug lah. Right, that's why I didn't do that lah. But if you want to run it on Google Colab, just directly get it from the Silicon Initiative, or I paste it here lah. Run this link that I just put in the chat. Run this link directly. Then it will work. But if you
Oh.
download this file and then you run on your own Google Colab, it won't work lah. Why?
Oh.
Because the thing is, this Google Colab, the way it works is underneath actually it's a virtual machine. There's a particular Linux distribution with tools and all that lah. So for some reason, Google already set it up, but I don't know how to get that particular machine. So I've only been able playing around. I've only been able to get it to work on this path lah. So you can update it all here, but the problem is after you do that, the next time you come in, you have to like redo it lah. It's not savable lah. But maybe what you can do is you can copy into a text file and then you just paste it back later lah. That would be a shortcut trick lah. That's one of the reasons why I built the Docker lah, because you know, I was foreseeing this, so that's why I spent about 2 weeks actually just building the Docker and debugging it lah. So I'm glad that you got it working on the Docker. If you got it working on the Docker, then just use the Docker lah. But if you like to know why, use this particular path lah, because it's just the what they call the runtime lah. What is the underlying tool? So I had no time to debug this particular one, what is missing and all that lah. Because I'm not so familiar with the Colab on the underlying. I don't have that low level control and don't have so much of time to go and debug it as well. Docker I'm a bit more familiar, so I could debug it faster lah.
And also just to share with you, it also happened when I tried to run the file that you share for in the ULENX using the Jupyter notebook.
Yeah,
it happened the same.
It happened the same, yes. So what's happening is if you didn't set the tools right, there's no way you can open the file I share. The only way you can run it on any environment is you click the link lah. But I think Pirdaus has a lot of expertise setting up Anaconda and stuff like that, so he's able to actually set it up properly lah, right? So he was faster setting that up than the Docker lah. So that's why Pirdaus could get it working lah. But if he can share how he can do it, then maybe you can replicate it lah. My approach was the Docker because I was able to control the environment better lah. So that's the downside about these tools lah. Like you actually have to set it up quite well lah. So Docker or Colab actually is hiding a lot of that process, but the problem is, you know, I actually thought that if I download this Jupyter notebook file, it would work, but actually it doesn't. So the problem is I didn't have time nor the expertise yet to go and debug why the Jupyter notebook, because actually I don't expect this to happen. I mean, Jupyter notebook, it should work, but for some reason it's happening lah. So I'm not sure why. So I'm with you there. My only solution at this point is go to, if it's working on the Docker, of course it'll be much easier on the Docker because you can carry that anywhere with you. If you still want to use it on Google Colab, use this link which I sent to you in the chat box, or you can talk to Pirdaus to see how he has done it on Anaconda on his local machine. He probably can guide you much better than I can. Yeah.
Okay, one more thing, Doctor.
Yes.
Okay, when I successful run using the what do you call it, using the Docker.
Yeah.
In terms of the result, I'm for the GDS.
Yes.
I'm only I didn't get the graph.
Yeah, so that is the disadvantage of the Docker at the moment, because that particular Docker that I set up doesn't have the Jupyter notebook. Right, so I would actually need to add the Jupyter notebook so that you can actually plot this thing lah.
This thing,
you can actually plot
I think
this
the layout
thing,
is we can see the
Right.
layout, but only we cannot see the graph. We cannot produce the graph, is it?
Oh, you can't produce the graph. Okay,
Yeah.
I see. Yes, you can't produce the graph. Let me explain a little bit. Yes, there's a little bit of a change. You can't produce the graph because
the plot, is it? Inside the Docker.
Plot show, because the thing is the Docker currently, that Docker I didn't actually check properly whether I can get Jupyter Notebook. So it's actually like a command line tool. So the visual drivers are not set up well. So that's why the matplotlib plot show you can't see properly. The simplest hack actually is to plot it to a file. That means if you go to matplotlib plot to file. So instead of viewing it, you plot it direct to a file. So save plot to image file, right? So instead of you do plot, there's here where you do save fig, you can plot it directly into a PNG or PDF. Then you book up the PDF, you book up the PNG under Windows. That would be the fastest, easiest shortcut way to do it. The nicer way would be for me to actually go and fix the Docker and install Jupyter Notebooks so that you can actually run this on the Docker itself. Locally, you can open your browser and run this. I'm pending to do that. So the way I can actually suggest to you is you replace this plot show. You go to this site. Instead of, you can do this plot is okay, but you don't type plot show. You plot save fig lah. You guna this one, and then you save it directly to the file, and then you open the file and you look at it. So it's not going to plot on your screen, but it's going to plot on the file, and you can actually look at the file, and then that file you can also include into your report ke apa lah. That is the fastest way at the moment. Not to wait for me lah, but if you want to wait for me, then maybe in a week or so, I probably will be able to fix the Docker, hopefully lah, fingers crossed. So you can actually visualize all of this on the actual Docker container. I hope that's okay, Asri.
Okay, understood. Okay.
Okay, yeah, it's just the way the drivers and the visualization work lah. Because it's macam Linux command line, you can't see. So actually, I'm a little bit curious, like how come it can plot this lah? I'm actually very curious lah. But maybe another way to do it, you can also do is like this. Because this one, if you can see this, that means the IPython display is working, but this is actually plotting image file. So what you can also do is you can save plotlib, you save it to an image file with .png, then you replicate this command, image that PNG file, so you can actually view the actual plot, but not using matplotlib, you're using this IPython display using this command. So you use this image command, but with the file. So it's like you're saving this plot now as a PNG using this approach. Then you use this command, this IPython display image command. You open that PNG, but for this one, then you should be able to see also in the Linux. This is another shortcut way to do it because you have verified that you can see this. That means this display library is working. Displaying images is working. It's just that matplotlib is pyplot is not working because of the drivers and those kind of things. Yeah. Okay. Going to just make one more call for any further questions before we conclude the session for today.
Dr. Eric, can I ask?
Yes, Lukman, please.
Yeah, my problem is to understand, to benchmark whether my calculation is correct or not, because when I got the effective resistance and the capacitance, compare it with the logical effort method, it seems the numbers doesn't tally.
Okay.
So,
Lukman, in your case, can you send me a draft of your solution? Not a submission, you just send it to me on email. I'll look at it and I'll advise you. A bit difficult to see now, but let me advise you. Maybe I'll be able to pick up what's wrong. Show me your method, and then I can tell you, maybe give you some hint where to look.
all right, Doctor, I will do.
Okay.
And for the others, probably if you want to display, you use the X11 terminals in Windows. It's also easy.
Okay, great. Thanks, Lukman. So yeah, Lukman also is a expert on Windows. X11 is that method. I don't fully understand it yet, but Lukman probably, if some others, if they're curious, can they contact you for some help?
Sure. Maybe I will post something in the chat group.
You're most welcome. You can put it on the forum in ULEarn-X, or if you have something, then share me. I can post it on ULEarn-X. Then I think everybody can benefit from that lah. Much appreciated. Thanks, Lukman.
Doctor.
Okay, all right. Yeah, so just send me your draft, and I'll look at it, and hopefully I'll be able to comment lah. But I'm very happy you got to the point where you can actually compare lah. So that's great. That means this you've managed to achieve it. The goals of it. You just have to check for accuracy. Yeah, good. One thing, Lukman, you also have to be careful because one thing to check lah. The inverter is actually driving 4 inverters, so it's a fan out of 4 delay. Whereas if you do the MOSFET, that inverter is not driving any load except its own junction capacitance. So the capacitance is largely different. So in the case of the analog inverter alone, you are probably only driving the junction capacitor, the 2P or the 3P there, 3 parasitic, whereas for the fan out of 4, you are driving 4 times the input gate capacitance plus that parasitic capacitance. So if you really want to normalize it, the analog one must actually be driving 4 inverters. Then it should be the same. That's the first thing to check, right?
Yeah, Doctor.
Yeah.
Will do. I will share to you. And
Yeah, you just share with me lah. Then
yeah.
I can discuss it with you.
Noted. Thank you.
Okay. All right. Final call for questions. Okay. If no more questions, then we conclude for tonight. Thanks for your active participation. This concludes the aging part. My recommendation is please spend the rest of this week preparing very well for your tests on 18th of November, this Saturday, 2 to 4 p.m. If you have any doubts in the interim, please post them on the WhatsApp or on the MS Teams, or send me an email. I'll try to get back to you as soon as I can on that, especially for test 1. And for test 2, unfortunately, you have a bit of a short time to pick up the aging stuff, but can't be helped because we have been delaying a lot of the work. But again, if there's any doubt on the aging after you reviewed the material, please let me know. And then as for practice, I recommend you just pull out some elementary logic gates and practice like deriving and calculating the values and reasoning around that. That would be a good way to practice for the aging analysis, right? So with that, wish you all a good night, and let's continue to keep in touch on WhatsApp if you have any doubts. Tutorial 2 times we extended to 3rd of December. So your test 1 will be on 18th November, test 2 25th November. Your PBL 2 will be due on the 26th of November. And then after that, I'll probably have another 1 to 2 more sessions to go into detail all the questions on test 1, test 2. But I will aim to grade it all first and return you the answer scripts at the same time with the discussion. Okay, so that you actually have at least about a week to revise all of that before final exams. I think it's on the 10th of December, right? Okay, wish all of you a good night, and take care. We'll continue to keep in touch as we try to conclude this semester.
Thank you, Doctor. Good
Thank
night.
you,
Okay,
Doctor.
thank
Good
you.
night, all.
Thank you. Good night, all. Bye.
Thanks, everyone. Goodbye.